Hello. This is going to be a week in which we look at energy, actually measure energy, different kinds of energy. Kinetic energy, for example, or gravitational potential energy, or in fact the energy, or in fact also work, which is a form of energy, and work is the energy that's done by a force. So we looked at Galileo's forces, measured forces last week, did Galileo's experiment. And in fact, when he dropped the ball off the Leaning Tower of Pisa, he had a ball at a certain height above the ground, and that height above the ground is measured by gravitational potential energy, because you're in a gravitational field, and when you're higher up, you have more potential energy than when you're lower down. And when he drops it, when it gets to the ground, it has turned all of the gravitational potential into kinetic energy, and it's going quite fast, by the way, when that ball reaches the ground from the height of the Leaning Tower. So let's, and we're going to do one simple experiment, and I want you to do this simple experiment very cleanly, because from this you can branch off and do many other things. So let me first off just talk about energy and work. So work is, as we'll find, as can be a force times a distance. So in Galileo's experiment, the force was gravity, and the distance was the height of the Leaning Tower. Okay, and that leads to a change in the work. Force times the distance is a change in the potential energy. So it changed the potential energy from a large number down to 0. Okay, so that's energy. That's work. But now look at energy. There's two forms of energy. There's kinetic energy, and then there are potential energies. Now, there are as many potential energies as there are forces, because every time there's a force, there's a corresponding potential energy. You just have to move around in the force field, and you change your potential energy. But now what is kinetic energy? Is very familiar and very obvious. Kinetic energy, which we'll denote as Ke, is the energy of motion. Okay? Now, it could be the motion of anything. It could be the motion of a ball, a car, a locomotive, or it can be a photon of light, okay, that also has energy, kinetic energy. It can also be a field, like an electromagnetic field, like a light wave, for example, also carries kinetic energy. So here's a locomotive, old-fashioned locomotive, has a huge mass, and it can crank itself up probably to 60 miles an hour or so. So velocity is 60 miles per hour. So the kinetic energy, there's an expression for the kinetic energy. The kinetic energy of that locomotive is 1/2 times the mass of the locomotive times its velocity squared. Okay? So you can see, since you square the velocity, the kinetic energy goes up fast when the velocity goes up fast. So that's direct kinetic energy of a huge mass. Now suppose you have, for example, a container full of air. Okay, could be the room you're in, has a bunch of air in it, right? If the air is cold, then the molecules, little blue things here, are moving around rather slowly, relatively speaking. And if the air is hot, at a high temperature in your room, then the molecules are moving around with a much higher velocity. The velocity goes up. So now the total kinetic energy of the molecules of the air in your room is going to be 1/2 mv squared, where m is the mass of a molecule, an oxygen or a nitrogen molecule, and v is the velocity. So as you raise the temperature, the velocity goes up. Okay? So the total heat energy in the room is 1/2 mv squared, just like the locomotive. Okay? But you have to multiply by the number of atoms in the room, which is a very, very large number, like Avogadro's number. Now, how do you know what this kinetic energy is of molecules? Well, it's the temperature. If you measure the temperature of the air, that tells you what the kinetic energy is of the molecules in the air. Now, that works also for example, here you have some, you can have a solid, you can have a liquid, or a gas. So we already discussed the gas. At the higher temperature, the velocity is more, kinetic energy stored in the gas is higher. For a liquid, of course, the molecules are closer together, but they're still moving around a lot. So at a lower temperature, you get a liquid, And the molecules are still moving around, but just not as fast as they are in a gas. And you go down to an even lower temperature, you end up with a solid. So the simplest the simplest case to think of here is water. So when water is frozen, it's ice. When it's between 0 Celsius and 100 Celsius, it's a liquid. And when it's above 100 Celsius, it is a gas. So it's just all the same molecules all the time. It's just that you change the temperature, you change the velocity with which the molecules are moving. So even in a solid, the water molecules are still moving around. They're just jiggling around in place. And the jiggling velocity is a measure of the temperature of the ice. Okay? So now here's a figure that's from the textbook here, and maybe it's a little bit too much to dwell on too much, but this is a universal figure that tells you almost everything you need to know about atoms, the mechanical properties of atoms, I should say. If you take two atoms, this is the kind of hand-drawn things here, which have a nucleus in the middle and a green electrons swirling around, so there's two atoms. Those two atoms, next to each other, they're constantly jiggling like this, okay? I mean, they're in a solid here, so they're not going to move out of the place, but they're just jiggling in place. And there is an expression that gives you the energy of those two atoms, the energy. Now, those two atoms, and it could be two side-by-side atoms in the ice here, in the solid. Those two atoms would like to sit at a separation in which the energy is a minimum. That's the fundamental fact of nature. Systems like to reach their point of lowest energy. They don't want to have too much energy and so on. It's too expensive. So they sit at a location, a separation, which is denoted as little a here in this figure. That's the equilibrium separation. So the molecules in ice, for example, will sit that distance apart, and they'll jiggle around that position. Look at what happens down here. Go down to the bottom of this energy curve here. It's called potential energy, by the way. Here's the separation of the two atoms is A. If the separation gets a little bit larger, then you have to climb up a hill. You have to climb up this energy curve, which is the red curve. If they jiggle to be a little bit too close together, the energy also goes up. So whether you jiggle closer together or farther apart, either way you lose, the energy goes up. So you have to go back down. So that's why these atoms oscillate in place. So this is exactly the same thing as a mass on a spring that oscillated. And you remember doing that, I think, in the second week when we made a clock out of a mass on a spring. It's exactly the same equation, exactly the same motion, by the way. It's not really a different thing. So the climbing up the curve is added potential energy, because this is a potential energy curve. And climbing up either end, the potential energy increases. So there's an equilibrium point at the lowest possible point. So atoms in a solid, for example, they have both kinetic and potential energy. Okay, and the potential energy here is the minimum. So let's go on here. What are the potential energies here? So it says here for every force, there's a corresponding potential energy for that force. And it's always this simple, okay? The force times the distance that the particle moves, that the object moves in the force field, that's called work. And work has the same properties as energy, okay? So okay? And so, for example, so let's list a bunch of forces. Here's the force of gravity. That's what keeps you in your seat, okay? The force is m times g, your mass times the acceleration of gravity. That's the force that holds you down to the surface of the Earth. The gravitational potential energy is the force times the height. So if you raise yourself up, you get, if you climb up, if you're sitting down in your chair, if you stand up, you're raising your mass up a couple of feet higher. So h is like 2 feet. So you have gained gravitational potential energy. And if you doubt, and it took you work, by the way, you had to exert a force, your legs had to exert a force to lift you up, and they did. So now you have more gravitational potential energy. If you doubt whether that's real energy or not, all you have to do is let yourself fall back into your chair, and you'll see that you had energy, okay? There's an electric force, which, by the way, we never really explored 2 weeks ago, but it's the charge times the electric field is the electric force, in the same way that the mass times the gravitational field is the gravitational force. You can talk about an electric field, and we didn't, but still. So the electric potential energy is the charge times the electric field times how far the charge moves inside the electric field, d, little d, okay? Well, how about a friction force? Now, we're going to study friction forces, okay? And friction force is the coefficient of friction times the normal force, written here as capital N. So the work done by friction is the friction force times the skid distance, and that's denoted as a little s, okay? That's a friction force. So when you're traveling 60 miles an hour and you have to stop fast, what you do is you put the brakes on, and that turns on the friction force. And how long a distance it takes you to stop is called the skid distance, s. Okay, and so the work done by friction has to be enough work. The total work here has to be enough to bring your kinetic energy, which was 1/2 mv squared, and v was 60 miles an hour, say. It has to be able to bring 1/2 mv squared down to 0. In other words, when your stop velocity is 0. So the friction force has to be big enough to do that, all right? And the stopping distance has to be long enough for you to do that. So that's a stopping problem. Now there's also a spring force. You remember you pulled on the spring, there's a force, right? And that force was some constant called the spring constant, K, times the stretch distance, X, all right? So now it turns out that the spring force depends upon the displacement x, unlike the other ones, other forces. So in fact, the spring potential energy turns out to be 1/2 k times x squared, all right? But it's still potential energy. Now they're rather more complicated. The interatomic forces, which are basically electrical in nature, because the electron is negative and the proton and the nucleus is positive, and you put two atoms together, they're forces. They're electrical forces. These lead to chemical potential energies, for example, in a battery. Okay, then there are nuclear forces between the nucleons, and this is nuclear rest mass energy, which is also a potential energy. So in mathematical terms, and you can turn off here for a minute if you don't like mathematical things. In mathematical terms, the change in the potential energy, call it delta E, the Greek letter delta E, is equal to the force times the change in distance, delta X. So if you have a force F, acting on some object, it could be your car, for example, or a marble. If you change the distance, you change the location of the object, you will change its potential energy by delta E, where delta E is F times delta X. Okay? Now, for simplicity, we can easily work with gravitational potential energy, kinetic energy, and work done by friction. Those are the three easy ones. So that's what we're going to do. Okay. Now, this problem of putting your brakes on and coming to a stop over a skid distance s, that's a classic problem. That's called the stopping problem. It appears everywhere. How do you stop a car? Well, you put a friction force on, and it brings you to stop in a certain distance. How do you get the space shuttle out of orbit? The space shuttle is many tons. It's traveling 18,000 miles per hour in orbit around the Earth. How do you ever get the shuttle back onto a runway in Florida at 0 velocity? How do you turn all that kinetic energy down to 0? That's what you have to do. And they basically use the friction of the air and the atmosphere to do that. It takes 1/2 of a turn around the Earth, that long a distance, in order to bring that kinetic energy down to 0. So that's the stopping problem. How do you survive a head-on collision on the highway? Well, you know, automobile manufacturers, after Volvo started this, put crush zones in cars. So there's a crush zone. The force of deceleration acts over a couple of feet, and that makes the average deceleration force less because it has a longer distance in which to act. How do you jump out of an airplane with a parachute and survive? Well, the parachute provides a friction force, all right? And over a long enough distance, that slows you down. How do you land a delicate rover on Mars? That's another question. I mean, the rocket that you send to Mars is going pretty fast, and you have a rover which you toss out of the rocket, and it has to land on Mars without breaking to pieces. How do you slow it down? Okay, that's another stopping problem. And then later on, we'll do the so-called egg drop experiment. How do you drop an egg inside of a package you will make? How do you drop it, for example, and have it hit the ground without breaking the egg? That's another stopping problem. So, in other words, how do you slow down and stop a mass m that's moving with a velocity v, and how do you lower its kinetic energy down to zero? So the kinetic energy has to equal the work done, which is the force times the distance, and the force is the friction force, the slowing down force. Okay. Now, energy has many different manifestations. There are many different kinds of energy. And this is one of the reasons why energy conservation was actually not understood for a long time. I mean, Galileo and Newton, they figured out motion and forces and all of that, but they didn't have a clue about energy. They couldn't figure energy out. It took a long time to figure out energy. In fact, one of the big clues came from actually biology. You take a human and you eat sugar and so on, it gives you actually energy, okay? Food gives you energy. And so correspondence was discovered between these two things. And then also Mr. Joule was making cannons for the British Army, and he discovered that the more you cut away the interior of the cannon, the more heat there was. So he found a correspondence between mechanical work and heat. And then he discovered that heat is actually energy too. So anyway, there is a principle called conservation of energy, or energy conservation. It says that the total energy of a system is exactly constant. Whatever energy you have, whatever form it's in, that amount of energy is constant. It doesn't change. It doesn't get bigger, doesn't get smaller, never gets lost. So now this is, let me do it in the simplest sense. You have to, this big circle here is meant to be a closed system, And there's no energy comes in and no energy goes out. Okay, so we're going to call that a closed system. It's an idealization, but it works fine. So suppose within that closed system, you have some gravitational potential energy. It might be, for example, a big rock that's 10 feet high. Okay, if you drop the rock, the rock will then end up down near the floor with kinetic energy, 1/2 mv squared. It hits the floor, and the floor heats up because all the kinetic energy went into heat. Now you can take that heat and put it through a heat engine and, for example, make a motor. For example, the engine in a locomotive is a heat engine, right? It turns heat into rotational kinetic energy. So now you have a shaft turning around and around. You can take that rotational shaft and make it run a generator, charge a battery. So now you have chemical potential energy. And that chemical potential energy, for example, can go back into a motor that lifts the mass up, okay? So now you turn it back into gravitational potential energy, okay? So in this whole business here, changing one kind of energy into another by various different engines and various processes and gadgets and so on, means that the total amount of energy is never lost. Now, in all of these processes, none of these processes are perfect efficient, perfect in every respect. So there's a lot of waste heat, okay, in all these processes. So everywhere along the line, you end up with some heat that gets discharged. But that heat is energy too, and as long as it's still inside the system, as long as you count it all up, you don't lose any energy. Okay, this is a really fundamental principle here. It's really very deeply fundamental. It's conservation of energy is equivalent to, at the very bottom I have written here, the symmetry of physical law under a time translation. It's a fancy way of saying that the laws of physics, whatever they are, don't depend on time. If you do an experiment today and tomorrow or 1,000 years from now, you're going to get the same result, okay, under the same circumstances. So that's a little exotic, but it's in a practical sense, energy conservation is vital, okay? So let's take a system, a really complicated system. That's the Earth. Now, the Earth is not exactly a closed system, but there's an energy balance. As long as the temperature of the Earth remains constant, then you know that the energy comes in from the sun in the form of light, okay, coming in from the right-hand side, and it shines on the Earth. The Earth is spinning, so it kind of heats up 1/2 of the Earth at any one time. And then the Earth has the light that goes out from the Earth, both in the visible and in the infrared. It's called albedo. It's called the albedo of the Earth. And you can see, by the way, cloud cover. Cloud cover is white, and that's because it's emitting all the wavelengths of light. That's white, right? And the oceans are blue, and so on. Okay. In fact, you even see a little tornado off the coast of Mexico. I never noticed that before, but in any case. So the Earth is a very complicated system. You can think of it as a closed system because the energy in is equal to the energy out, and so it remains in what we call equilibrium. Okay, which means that the processes inside the Earth may be very, very complicated and changing all the time, which, by the way, it is. But the average temperature doesn't change, which means the average kinetic energy of everything on the Earth, the average, doesn't change. It goes up and down hourly, by the minutes, by the year, but the average never changes. Okay, so that's a lecture on energy and so on. So let's do an experiment. We'll be talking about gravitational potential energy, which you'll write GPE, and that's going to be the mass of the object times the acceleration of gravity g times the height that's at, mgh. That's gravitational potential energy. We'll use kinetic energy, which is 1/2 times the mass of the object times its velocity squared. And the work done by the friction force, we'll call it W, which is going to be friction force, always written as a little f, times the skid distance, s. Okay? Now the experiment we're going to do is probably more accurate than the experiments that were done by Joule. Okay? And by the way, the unit of energy and work is called the joule. That's the unit that's used. There's an appendix in the textbook on all the units that are used in physics, and joule is the unit for energy. So now here, what do we need? We're going to do one experiment, and we're going to do it carefully and completely. And I encourage you, by the way, to go beyond this if you so choose. So the supplies you're going to need are all in your box, plus 3 pieces of computer paper, nice high-quality smooth paper. And then here, under here, there's your steel ruler under there, which came in week 1. There's a marble, which should be in this week's envelope, I think. And then there's I put a paper trough here so that the marble will roll down this ramp supported by this steel ruler, and there'll be very little friction. Okay, so the friction force along here is going to be almost 0. Then there's going to be a piece of wood here. Okay, a pair of scissors, and then another ruler if you like. Okay, so I had another plastic ruler around, which I'll use this ruler. But in week 1, we used our hand to measure. So you can also use your hand if you're confident doing that. And then here's a little it's a paper wedge, which is going to be providing friction. Okay, this paper wedge on the computer paper underneath it will provide a small friction force, small constant friction force. Okay, so here's an introduction to that, a video here, and I'll play it now. Okay.
Hello, this is the setup that is in the recorded lecture. So let's just demonstrate it once, and then we'll discuss what it is. Here's a marble, and here's a ramp, and then here's a paper catcher. Okay, and let's first off see how it goes. Just do a trial run. There's not going to take any data here. We let the marble go down, and there you go, and it skidded this far. So we can put this little red marker here where it stopped. So it started here, went to there. So this is the experiment we will be doing. Okay, and then what we'll do, then we'll measure with a second ruler. This is the metal ruler in your kit. We're going to measure the distance, the skid distance here, how long it took to skid to a stop. Now, what we have here, first off, this piece of wood, this is ash actually, which is a nice smooth hardwood, and it's cut like this. So we can raise this ramp, we can raise this end of the ramp by 3 amounts. We can raise it by this amount, we can turn the block this way and raise it by this amount, and we can put the block this way and raise it by this amount. So we have 3 different heights that we can raise the ramp to. So let's first off put this way, and I will measure these 3 distances with the ruler we have here in centimeters. Okay, so first off we put this here. So we have a rather gentle ramp here, and And then the ramp itself, which is, I just took the ruler we have, metal ruler, and made a trough, okay, just out of paper, and I taped it on both ends. So the marble now has a nice smooth run down, and there's basically no friction there. And then this, then I put this little wedge, the skidder, I'll call it here. I'll put it here so it'll catch with its apex right at the little line here, which is my measurement, and then we let this go down. So let's go, we'll do that one more time, and you'll see it goes that way. So now actually you see it went a little farther than the previous time. I don't have an easy explanation for that, but that's what it did, okay? Now, so let's just take a mental note here. This went about 12 centimeters, okay? 12 centimeters of skid. So let's, for fun, crank up the height, okay? So make the height bigger here, and then we'll do the same again, and we'll see how far the skid distance is. Okay, skid distance now looks like it's about 23 centimeters, okay? So we started out at a higher height, so the gravitational potential energy was more, at the bottom the kinetic energy was more, and it skidded a longer distance. So that, and now just one more, just to show you the third one, we're going to raise it up really high, the height of this. So we're going to have to back off here because we're going to need more skid room, and I'll do the measurements later. And so here we go. We put this like this, and now I think I have enough room out to here. I just put paper down, so we'll have a nice smooth surface because this wooden table is not that smooth. Okay, so here we go. Went that far, okay? So this is about 30 centimeters. This is about 60 centimeters. And to here, 68 centimeters total, okay? It went 68 centimeters. And so that's the total skid distance, you can see. So now so now we're kind of ready to do some measurements, right? So I'm going to, as a good experimenter, I'm going to keep some notes, and let me keep from your laboratory notebook, which you should be using to keep notes. I'm going to measure the mass of the marble with our electronic balance that we used on the first week. With a ruler, I'm going to measure the height of this, okay? And then G is the acceleration of gravity, that's 10 meters per second squared, okay? So we know mgh, and that's the gravitational potential energy we started with. As it rolls down, now when h is now 0 just at the table height, it will have a kinetic energy which should equal mgh, and then it'll skid through a skid distance, so there'll be a friction force here, a constant friction force, and it'll skid a certain distance, s, we'll call it the skid distance s, and so the friction force times the distance is the work that is done by the rolling marble, and that friction force should actually equal the kinetic energy at this point and equal the gravitational potential energy we started out with in the beginning. So I'm going to do several trials. I'll just say 5 or 6 trials, maybe 10, and then I'll average them to get an estimate. You saw that we made 2 measurements, and both of them differed by a couple of centimeters. I don't know why. I'll try to keep the conditions the same so we have reproducible results and get say, for example, a good average. So that's the experiment for this whole week, okay? Now, so I will go make a bunch of measurements and then present the results to you in the recorded lecture. And then this is something you can do. You need 3 pieces of computer paper, scissors and the tape, and maybe an extra ruler. But in week 1, we developed ways to measure distances with our hands, so you don't even need a ruler if you want to do this and this, okay, and so on. Okay, so there you go. So I'll do several runs, get an average. I'll record the results and show them to you later on. Okay.
Okay, so I just did several runs of each height, and here, for example, if I just hold it up here, I measured the mass of the marble on the electronic balance that you have in your week 1 folder, as 3.54 grams. The height of the lowest for the block is 1.1 millimeters. Where's that block? Yep. So this is 1.1 millimeters. And okay, and acceleration of gravity is 10 meters per second squared. So I did 10 trials here, and I got 13 centimeters, 12.2, 11.4, 13.5. Some variations here. Okay, one as high as 14 centimeters skid distance, and I think the shortest one was 11, and the longest one was 14. Okay, but anyway, the average is 13.1. So 13.1 centimeters is the skid distance if your ramp is as high as 1.1 centimeters at the end of your steel ruler. Okay, and then I went to the this height, which is this height of the for the block is 1.9 centimeters. I measured it very carefully with a millimeter ruler, and I only did 5 because they looked fairly consistent here. 24.7 and then 23.9, 24.8, 25, and the average is 25.0 centimeters. That's the skid distance. Yes, the average skid distance for a ramp height of 1.1 centimeters. So, and then I did the long one. Okay, let's see, where's that? Let's see, I kept a lot of my notes here for the height. When the height of the ramp was 6.32 centimeters, and that's in fact this height. And I took all 3 pieces of computer paper. That's the skid distance. So I got skid distances actually very close to each other, 73, 74, 72, 74. And then one really low fluctuation like 60, 67. I had to leave that one in there. There was nothing I can tell that was wrong with that compared to the other ones. So I averaged them all. 72.1 centimeters is the skid distance for the ramp this high. Okay, so and then I made a little summary of everything. Now a little algebra here, okay? But in any case, the basic equation is that the energy, mgh, gravitational potential energy at the beginning, it will equal the kinetic energy at the bottom, but we don't measure velocities here. We could try, but we don't. But that should equal the work done to friction, the friction force times the skid distance S. That's what it should be in the end, okay? And so that means that, for example, the skid distance will go like mg times the height of the ramp divided by the friction. Now, the friction is kind of the same, okay? I mean, it's the same piece of paper all the way along. So the friction force should be the same. That means that the skid distance should go like the height. So if you have twice the height, you'll have twice the skid distance, okay? You can also take this formula and turn it around and say, what's the friction force? You didn't measure a friction force here. What is the friction force? Well, that'll be mg times the height divided by the skid distance. So as the height gets bigger, the skid distance gets bigger, but in the same proportion. So the friction coefficient of this little skidder on the computer paper should not depend on the height. Okay, so I made plots of that. Maybe I should have got another one. Made plots of that here. Here, for example, is the height. So we have 3 heights, 1.1, 1.9, and 6.32 centimeters. And here's the skid distance in centimeters. And here's the 1 point, another point, and another point. Now, a 4th point is 0, because when there's 0 height, there's 0 skid distance. So 0, 0 is a point. And you see it more or less goes through all 3 points. I mean, not exact. It's not really precise. There are a couple of odd numbers in there where I wasn't sure of, but but that's a linear relationship that you expect. Higher ramp height, longer skid distance. And then I also, a little screwed up here, but this is the friction force in units of millinewtons, okay, a thousandth of a newton. And here are the 3 heights, ridge heights, 1.1, 1.9, 6.3. And here are the 3 friction coefficients, are each all around 3, 2.97, 2 point something. Okay, 2.69, 2.69, and 3.1. They're all pretty much independent of the height, okay, as they should be, according to our formula. So here's a little summary table of the numbers I got, okay? Now, okay, so here's the height, the average skid distance, the friction force in newtons, and they're all 10 to the minus 3, so that's a millinewton. So here's the friction force in millinewtons, okay? So that's the complete thing here. Now, I'd like you to do this experiment because I'd like you to get children to do this experiment someday, so you should do it. You don't have to be, making a table and plots and so on, but I think for the higher grades, it's nice to see a plot. When one thing gets bigger, the other thing gets bigger, as it should, linearly. Double one, you double the other. Those are important concepts about understanding numbers and data and everything, even in third grade, I say. Okay, but I'm not a teacher, so I really don't know. So that's this experiment. I encourage you to spend a little time. Like I said, I only went through this once. If I were really in this business and my life depended on it, I would repeat all of these experiments. Tomorrow, the next day, I'd be very careful. I noticed that sometimes the skid would, instead of going straight forward, it kind of angle off to the side a little bit, and I wondered whether or not that would give me a wrong reading for the skid distance, and so on. So there are lots of little things to worry about here, but that's what I found. So now let's go ahead and take a look at the kinds of things you could do in a classroom if you have a big table and you have a couple of long boards and so on. So let me quickly go through those because you won't be able to do those here. Oh yeah, well, I'm sorry. Here's what we just did. Okay, a drawing of it. Here's a marble, mass M, height H. There's the ruler ramp, and this is all on a desk or a tabletop. And then the marble rolls down, and it has a velocity v at the bottom. It has a kinetic energy, which is 1/2 mv squared. And then it gets captured by the skidder, okay, still at velocity v. And there's a start point, okay. And then there's a friction along the table. The skidder has a friction, and it slows down and it stops, okay. So that's so there's a skid distance S, and that's what we measured from the start to the stop, the skid distance. Now on the very bottom is energy. The energy never changes throughout all of this, okay? The energy is mgh to begin with. That becomes 1/2 mv squared when the marble's at the bottom of the ramp. And that becomes the work done to friction, the friction force times the skid distance. All three of those numbers are the same. There's one small proviso I didn't throw in. The kinetic energy is not only linear kinetic energy, but it's also rotating, so there's rotational kinetic energy in there too. But that's the total kinetic energy. All right, so that's what we just did. In a classroom, you can have ramps that are, so for example, 3 feet long. Nice wooden ramps and so on, and you can have a height H, which is 20 centimeters, and you can put a car up there, okay, a toy car. And then the same thing is true, all the same thing. The toy car comes down this way. By the way, there's friction in the wheels of the car, so this is actually more complicated. There's friction down here, there's friction along here. So here it comes down, and it goes a distance s at velocity v at the bottom, and then it skids along here and eventually stops when the kinetic energy is 0. So basically the total mgh you started with ends up as friction. The friction force times s plus the friction force times t. Okay. So so here's the same thing, by the way, and I'm not going to go through this, I guess. It describes the same thing you can do with toy cars. And so at the very bottom it asks the question, we started with mgh of energy and ended up with nothing, in quotes, nothing. Well, actually, where'd the energy go? Well, it went into heat. Now you can't measure that heat very well, the heat of the friction force, but actually it ended up in heat. Now in the lab, actually, where did all the mgh go? Well, I bought a couple of very expensive, they're $250 a piece. They're infrared cameras, which you can attach to your cell phone. And they actually see infrared light. They measure infrared light, and you can see heat. So you take a at night you take an image of a house, and you'll see that all the windows are all bright, because that's where all the heat is. The heat loss from a house is in the windows, not the walls. Also, the hot brakes on a stopping bus, or even you can put your hand on a table, then take your hand off the table and take an infrared image of the table, and you can see the heat imprint of your hand. Okay? And you can also, even with a little difficulty, you can measure the heat from the friction of one block on another block, and so on. So it's very nice, but it's a little too much sometimes maybe for elementary school, but I think in 5th or 6th grade you could. Now, the other thing you can do, in addition to, you can have a toy car. Here's the same experiment. Toy car goes down a ramp, and then it skids to a stop due to a friction. But you can use a wooden block too, and I was originally intending for this wooden block to be used in the lower figure here. So you can have the wooden block has friction on the surface, and so it does the same thing the car does, except you have to start out with a higher H because the friction forces are larger, so you want to have a stopping distance that's not too small, and so on. So you can do the same experiment with a wooden block. Okay? All right, so that's all of the energy conservation, but I encourage you to do the simple one with a marble, and with all of the things you have in the box. You don't have to have anything else except scissors and so on. Now, there are other things here, lots more things about energy, machines that do work, and I'm going to go through this very briefly. There's a lever. You can use a lever to lift a very heavy weight by applying a small force. Okay, that's what a lever does. There's the wheel and axle. There are pulleys. There's the inclined plane. Okay, you can pull an object up an inclined plane using a smaller force than what you would be required to just lift it directly up. There's the wedge. Anybody who's cut wood, broken up firewood with a wedge appreciates a wedge. There's a screw. Okay, all of these are called the 6 simple machines. Now, here's a ramp. By the way, this is behind the physics department. It's on the loading dock. Okay, here's a ramp, a nice gentle ramp. These are levers. They have various names. There's a class 1 lever, a class 2 lever, and a class 3 lever. It depends on where the fulcrum point is. That's the difference. And so your arm actually has a so-called class 3 lever. Okay, the pivot point is the joint here, and your muscles here are the force, and you can lift mg in your hands. Okay, so, and then these are pulleys. You can lift you can lift a 100 Newton mass force by only exerting 50 newtons if you use a pulley. If you use 3 pulleys, you can lift 100 newtons with only 25 newtons of force. Okay, so that's what pulleys do for you. Here's a bicycle, by the way. Bicycles actually have 3 or 4 different of these basic machines built into a bicycle. Bicycle is very efficient. Here's the screws. Okay, here's the over by the bus station beyond the power plant on ISU campus. There's a wind turbine. That's a screw. Here's the wood screws here, and here's a worm gear, which is also a screw. All of them gain mechanical advantage. Here's a wedge. A vertical force down gives you huge sideways forces which split wood apart, for example. Okay, here's the last one. Activities for this online lab at your desk. Okay, just what we did, by the way. Here's activities for a future classroom, which I won't go through, but hopefully someday you'll do this experiment in your classroom, and you'll be able to do wonderful things. If even very good quantitative experiments you can do. So you set up the metal ruler as a ramp, and a paper groove for the marble. You fold a paper wedge, which we called the skidder. And then you measure the stopping distance of this skidder wedge for several times and take an average, okay? Then you can make the ramp steeper and also measure the stopping distances, and then keep a notebook, okay? And make a plot of the wedge height versus the stopping distance, okay? So that's it. I'll see you Monday, which will be tomorrow, Monday at 3:20. And you come with questions. I'll go over this or answer any questions you like about anything else on here. Okay, thank you very much. See you soon.